Hi everyone, this is Vamshi, having roll number 04 MCQ from the ECE section. So today I want to discuss about the difference between analytic and differentiable function under the subject complex analysis and special functions. So coming to the our first topic as a differentiable function. So a function when it is called as a differentiable function f. So a function f is differentiable at a point x naught if it continues at x and there exists a limit of the differences quotient as limit extends to x naught f of x minus f of x naught by x minus x naught. So if any function which satisfy these two conditions, it is called as a differentiable function. A function f is called differentiable in I if it is differentiable at every point x naught which is belong to the interval of I. So when it's a function different over its domain. So but how to check if a function is differentiable at x naught? So if I have a lot of function, check if x naught has exactly one tangent, and in general cases check if f is a continuous in particular no jump, and check if limit x naught extends to x naught and x less than x naught, where f of x minus f of x naught by x minus x naught is equal to limit extends to x naught x greater than x naught f of x minus f of x naught by x minus x naught, and both agree. So in general case we have to check that limit of a function under the condition x tends to x naught and x minus x less than x naught, and also which is equal to x tends to x naught and x greater than x naught. So if these functions exist and both the exist, then the function is called as a differentiable function at x naught. So let us see some example for the differentiable function. First example is f of x equal to x naught. So this function f of x equal to x square, it is a function differentiable over R and have the tangent at the origin. And coming to the another example, f of x equal 1 by x. So it is differentiable over without over R except 0. So here you can see the plot of this function which is not differentiable at only x naught equal to 0. So coming to the f of x equal mod x minus 1, it is differentiable over only one except 1 point over the range of R. So another function f of x equal root x with x less than or equal to 4, and f of x equal x by 4 plus 1 with x greater than 4. So depending on the visualization, non-differentiable point might not be visible at all. So applying the definition to the function, let us see some example. By applying some example to define it is a differentiable or not. So f of x equal x square is an example. So applying definition like limit x tends to x naught f of x minus f of x naught by x minus x naught equal to limit x tends to x naught x square minus x naught square by x minus x naught, which is equal to limit x tends to x naught resulting as 2x naught. So the limit exists for all x naught. So this way this was very easy, but what about side x square? This is clearly the wrong way. So for simple variable function we can apply this function, but if we getting to the sine function, complex trigonometric function, it turns to difficult. So we doesn't get the any solution by using this function. So here you can see some general rules for the checking differentiability by notations like predicate dx naught if is differentiable at x naught, and di which f is differentiable over I is a interval. So coming to the function range function, like range of function f on the interval I. So dx naught of f equal to f of limit x tends to x naught f of x minus f of x naught by x minus x naught for x less than x naught, and d plus denote the x greater than x naught of limit function. So these were the two rules for checking differentiability, and some of other rules are addition, subtraction, multiplication, and division. So di of f plus di of g by d of f plus g, and coming to the subtraction, di of f di g by di of f minus g, and in the similar way we get the multiplication and division function. So, and some special cases we have di extends to x, where d1 of f by d1 of minus f, and d1 of sin x, and d1 of cos x. So coming to the another function, analytic function, a single valued function which is differentiable at each point of domain D is said to be analytic in that domain. So a function is said to be analytic at a point if its variable exists. So a function is said to be analytic at a point if its derivative exists not only at the point but in some neighborhood of that point. So the point where the function is not analytic is called a singular point of the function. So some of the noting points are, let f of z and g of z be analytic function in some domain D. So then f of z into g of z and f of z dot d are also analytic functions in domain D, and f of z by g of z is analytic in D except where g of z not equals 0. So if g of z equals 0, it tends to infinity, and f of g of z and g of f of z are also analytic functions in the domain D. So coming to the Cauchy-Riemann equation, let us see the theorem of the above Cauchy-Riemann equation. So let f of z equal to u of x comma y plus I v of x comma y be defined an open subset of U of a complex plane C. So if f of z is analytic in U, then U and V are differentiable and satisfy the Cauchy-Riemann equation. So it is tested by dou u by dou x equal dou v by dou y, and dou u by dou y equal minus dou v by dou x in the U. And conversely, if the partial derivatives of u and v exist and are continuous in U, and if the C2 Cauchy-Riemann equations 1 holds in U, then f of z is analytic in U. So if the function f of z is defined as u of x comma y plus I of v of x comma y is said to be analytic, and also it is said to be Cauchy-Riemann equation if it only satisfies the given equation 1. So here you can see the sum of the remarks. If f of z is analytic in U, then f dash of z equal to dou u by dou x into x comma y plus I into dou v by dou x into x comma y, and note that part B is not required the converse of the part A. So to be the true converse, we would need to add to a part A that assertion. F of z analytic, the partials of u comma v are continuous. This is true, but only we establish later. So f of z analytic, also f dash of z also analytic functions. So here you can see the proof for the Cauchy-Riemann equation. Let's take a complex number z. Since a complex number have both an imaginary part and a real part, let's write as z equal x plus I y. Next, let's take a complex function of f in the form of function as a complex number. So f dash of z naught equal limit z naught z tends to 0, where f of z naught plus delta z minus f of z naught by delta z whole power n. So should exist with delta z equal delta x plus delta I, and f naught of z naught can be computed along as c1 equal y equal y naught and x greater than x naught, delta x, that is delta z equal delta x, and similarly c2 equal condition 2 equal x equal x naught, y greater than y naught, and that is delta z equal to I delta y. So it is represent dou u by dou x equal dou v by dou y, and dou u by dou y equal minus dou v by dou x. So here you can see the sum of the expression like g of x comma y equal u of x comma y plus iv x comma y, and u of x comma y is given by x square plus y square, and v of x comma y equal minus y by x square plus y square. So we have derived the dou u by dou x and dou u by dou y. By comparing this, we can define the given function Cauchy-Riemann equation or not. So coming to the applications of analytic functions are commonly used in compute cumulative moving center and reported aggregation, and to calculate the employees under each manager.